Welcome, everyone. Today we're going on a little adventure. We'll be visualizing the third dimension by unlocking secrets of contour plots. Have you ever looked at a topographic map, the kind hikers use? Those looping lines that show mountains and valleys? That is a perfect real-world example of a contour plot. It's a magical way to take a 3D shape, like a landscape, and flatten it onto a 2D page, using lines of constant height. Let's sketch the contour plot for the function f of x, y equals 4x squared plus y squared. We'll use level curves for the heights k equals 0, 1, 2, 3, 4, and 5. A contour plot is a map of the function's output. Each line on this map, called a level curve or contour line, represents all the points where the function's value is exactly the same. Let's start with the simplest case, k equals 0. We set the function equal to 0. So, 4x squared plus y squared equals 0. The only way the sum of two squared terms can be 0 is if they are both 0. So, the level curve for k equals 0 isn't a curve at all. It's just a single point at the origin. Now, let's move to k equals 1. This tells us the ellipse crosses the x-axis at plus and minus 1/2, and it crosses the y-axis at plus and minus 1. So, we can sketch a narrow, vertical ellipse. Next, k equals 2. This is another ellipse. It's a bit wider than the previous one, crossing the x-axis at approximately plus and minus 0.7, and the y-axis at plus and minus 1.4. For k equals 3, the ellipse continues to grow. Its x-intercepts are at plus and minus root 3 over 2, which is about 0.87, and its y-intercepts are at plus and minus root 3, about 1.73. For k equals 4, this ellipse is wider still. It crosses the x-axis at plus and minus 1, and the y-axis at plus and minus 2. Finally, for k equals 5, this is our largest ellipse yet, with x-intercepts at plus and minus root 5 over 2, about 1.12, and y-intercepts at plus and minus root 5, about 2.24. Now, if we sketch all of these curves, from the point at the origin to the progressively larger ellipses, we have our complete contour plot. Notice how the curves never cross, and they get closer together as we move away from the origin. This tells us the function, which looks like a parabolic bowl, is getting steeper the farther out we go. The contour plot gives us a perfect two-dimensional map of this three-dimensional shape. So, to recap, a contour plot is a collection of level curves for a function. It's an essential tool for anyone working in mathematics, engineering, or data science to visualize complex, multidimensional relationships. Thank you for your time. This is K.Kumaravelu, hoping you now see the world of surfaces in a whole new dimension.